Hello, CNB 13, CNB 1311 again. All right, we're going to pick up with slope protection. This is civil engineering, structural engineering. Architects need to understand that they need this. They're not expected to do all the angle of repose calculations, runoff erosion calculations, water slowdown, water velocity, that sort of thing. But I'm going to give you a concept of why this is necessary. All right, let's say we have this slope, and it's a part of your topography. And you have if this is out in Arizona, you got to worry about wind erosion, all right, which in some places is almost as damaging as water erosion. But let's just say this is normal topography in a normal geographic ecosystem where we have water, okay? So water is very destructive, okay? And we got this, and we were doing some runoff, and it's coming down, and guess what? It's eating away. I mean, that's what made the Grand Canyon, right? All right, water erosion. So it'll strip all this off. Your soil, your dirt, your vegetation, if you're not careful, will end up down here someplace else where you don't want it. And your lawyers may not want it. Because if you're damaging somebody else's property because of something you did or did not do, that could open up for a litigious situation. Okay, let's double check, make sure this is running. Okay, good. All right. Now, so we need to create a series of terraces to reduce the velocity of the runoff. Now, that's what he's trying to do here. He's calling this a terrace. You've probably seen pictures of those rice paddies in China and other places where they're built on the side of a mountain, where they're hard terraces, okay, hard wall terraces, okay, and then they grow the rice up in here, and that holds the water and that sort of thing. Well, these little bumps might work on shallow sloped agricultural field. That's why we would call them windrowing when we were raising hay. But for commercial and residential construction, it doesn't work out too well. The principal mechanical means of protecting an embankment against erosion is a revetment, okay? This is referred to as riprap, okay? It's granular material. It can be crushed concrete, gravel. Sometimes it can be wrapped in wire, and it's laid in. There's generally filter fabric underneath here, which allows your riprap not to get mixed with your dirt, but it allows the water to go down and hydrate the soil if needed. Okay, all right. The depth and layers should be much greater than the maximum size of the stone. Well, that is very true. All right, but that's a riprap, okay? And it's usually broken or random size. I've seen them use the heavy wash stones where they want it to look cool. A lot of times you just broken up concrete. All right, this one here is cribbing. So we have riprap. You have cribbing. Now these are terms that you need to know where to find them. That's a hint. Like crib or a bin wall. All right. But if you'll notice, these things are stacked and interlocked, okay? It's they call it the cellular framework of squared steel, concrete or timber members assembled in layers at right angles and filled with earth or stones. All right, so actually this interior would be filled with granular material, hopefully not earth. You want the water to flow through here. And then you see this little hole at the bottom where the water would flow out. And then the artist that did this rendering, it was probably Ching years ago. They got a horizontal drain down here. I don't know why you would do that, but anyway, they did. This one is a bin wall that is a precast bin that basically are heavy blocks of concrete with a keyway. That little notch right there is called a keyway, and it fits in, and you stack. But you'll notice these have to be on an angle, right? These are on an angle, and they have a foundation underneath here, and you just can't build this like that. You have to excavate back out, and then you have to stack this and start filling in, backfilling, and you have to compact your backfill. So that puts pressure on all of this. That puts pressure on all of this to stabilize this slope protection. So theoretically your water would flow through here and drop, but then what happens if water drops too far? It'll start making cutouts and erosions and stuff like that. That's why Harris County Flood Control paves all this stuff with concrete. All these main deals, you don't see this. You see a bank, and this stuff is concrete all the way down to the lower channel on your big flood control ditches, right? Keeps that stuff from eroding. All right. But we're talking about something like this, okay? So we cut off and made terraces. But you got to be careful about your vertical velocity and how much water, because if you get a lot of watershed off of here, it's going to do something like that. It'll drop. When it hits, it'll start undermining the next cribbing or bin wall. All right. Next ones are gabions. Gabions have been used for centuries. It has been stated that gabions were invented by Alexander the Great as a barricade in warfare. Gabions have been used for centuries and centuries and centuries. Nobody knows who invented them. They're a basket or a meshed wire box that you unfold, and you fill them full of granular material. You fill them full of dirt, you can fill them full of sand, you can fill them full of gravel, stones, and then dry rods in them and stack them together. Okay. Again, if you're going to do this for true erosion control, you need really a fabric, a geofabric, geotextile behind it. Okay, this is your soil over here. All right. That way, the water, if it starts building up, can mitigate through there and hydrate the soil. All right. We use these over in the desert to protect against IEDs. They were big boxes, and we filled them full of sand. Those are gabions. And this diagram is natural means of stabilization, including soil or vegetation. And depending upon the slope, and your soils engineer and your civil engineer need to be addressing this. Okay, how much rain do you get? So how much water is going to be shedding off of this, and what's the slope, what's the angle, how fast is that water running down, the velocity of that water, what's the velocity of it traveling down. If it's too much, too fast, it'll erode your little Chinese jasmine or Japanese jasmine you planted for erosion control, right? Or if it's a tree even in here, it could erode the root structure of the tree. So, again, yes, vegetation can be used, just like hydromulching. Texas Highway Department uses hydromulching as a stopgap on the first end. Hydromulching, in my opinion, is a waste of money for getting vegetation to start on erosion control, but that's my opinion. For a quick spray-on surface to help after you first finish all your compacting of your slope, yeah, hydromulching is an option, but it's not a long-term solution. All right, so we have natural means of stabilization, soil binders, plant materials. Again, the smartest thing is to use your indigenous plant species. Go back to Frank Lloyd Wright's idea of the Usonian mindset of architecture and landscaping. If you have a lot of yaupon trees, and hardly anything kills a yaupon, then maybe build you a big nussle of yaupons and get them started. Those things are like bamboo. Some people use bamboo. Bamboo is an invasive species. Invasive, but it certainly works if done and designed properly. Now, I'm no horticulturalist. I'm just speaking from experience. Okay. So what happens is these roots will bind into the soil, right? Assuming that their water velocity is not so fast that it'll erode everything away. All right. Again, when a desired change in ground elevation exceeds the angle of repose, what's going to happen? Your soil's going to slough off. Okay? And you're going to have a retaining wall, which brings us to retaining walls. A retaining wall must be designed and constructed to resist the lateral pressures of the soil bearing retained, both the static soil and the dynamic soil pressure. Now, how is soil going to be dynamic? I'm not talking about an earthquake. I'll tell you in just a second. It's probably not in the book, but I'm going to tell you anyway. You paid money for this course. All right. So the pressure increases proportionally from 0 at the upper grade to the maximum. And that's what we're talking about here, okay? This is the soil pressure, all right, against the bottom of the wall, okay? The deeper down you go, just like water, soil and water is the same. Soil around here weighs about 150 pounds a cubic foot, which is the same as reinforced concrete. So so we don't really worry about it when we're excavating for concrete footings and we're putting concrete back down, because we're putting back down 150 pounds a cubic foot and we pulled out 150 pounds a cubic foot. There's no extra charge for that. But anyway, so the retaining wall, the highest pressure is down here and the lowest pressure is up here. Now, once this is compacted, and again, to build this wall, all this has to be excavated out, and this has to be put back in this soil, and it has to be compacted, which is an additional force on the retaining wall while it's being backfilled. Ching doesn't talk about that, I don't think, but I will. Some people get in trouble. They get too much heavy backfilling pressure, compacting pressure on these lifts that they're putting in. Sometimes they tend to overstress the retaining wall, or actually start sliding the footing a little bit, which is a bad thing. Okay, bad thing. All right, so all these are force vectors, and he's talking to you about where the center of gravity of the force is, which is 1/3 of the height of the wall. Okay, so 1/3 the height is the theoretical center of gravity of the force that's being pushed out that way. Now also, this is trying to turn this this thing around. It's trying to make it rotate about the base. That's called a moment. And we have a gravity force. And this little r vector is the resultant force. You take statics, which is in your pathway eventually. You'll have to take statics. Jared Kamen is teaching statics currently. He's a good engineer. He's done well. Okay, so that's a retaining wall. Okay, I do like these cantilever retaining walls. They're expensive, but they work. They're better than those all this other stuff. Okay. Here's another one. Okay, this would be a flat. This is a supercharged, so you got more moment, so we're going to have more concrete and reinforcing steel down here. It's an additional load. Now, the supercharged load means this stuff wants to slide down. Okay, it's pushing there. Now, what happens if we get water table in with this soil? Then this soil starts to bubble up a little bit, right? Like a flood or something. There's an additional load on the wall. Okay, that's what I'm saying about the live load and dynamic load. Okay, if this soil gets super saturated and it wants to like let go, it's exceeded its angle of repose, then this soil is going to want to move down, and it becomes more like a live load as opposed to a static load. Because when it's super dry, the weight of the soil at some point back here, based on the angle of repose, is just going to be vertical. But if it gets super wet and this stuff starts sloughing off, then you're going to have an additional load. Okay? All right. What's he talking about thrust? Why is he using the term thrust? Okay, all right, thrust, horizontal component. Okay, I got it. That's potato. All right, that's fine. All right. What at the center? This is the centroid, the center of gravity of this whole mess. Okay, the rule of thumb is 1/3 the height for this. All right, that means all of this weight is going to, this force from this stuff back behind it, is going to want to push it at that point, which means it wants to flip it. It wants to make it go this direction. It wants to overturn it. But you've also got the vertical weight on the foot, the weight of the wall, which is all combined, okay, so that we've got this vertical load, we've got this horizontal load, and then we've got the overturning moment, the rotating moment. And he shows the little MO over here as the moment, but it's really over here. But that's okay. This is not an engineering course. All right. But it's a good, he does a good job and always has. Like I said, I've got the first edition of this book. It was done in the early 70s. We used it in A&M, believe it or not. Another part of this is, will this thrust, this horizontal force, is it going to make this foot slide that way? We know it wants to overturn it, make it flip over, all right? But will it also make it slide? Well, we've got the resultant force of how much dirt is on the other side, the non-heavily loaded side of the wall that's pushing against it, plus the friction, soil friction on the footing. And sometimes you'll see some of these footings will have a big casting keyway, like a grade beam down here attached to it, to help key it into the soil, believe it or not. Okay, so he's using the term passive pressure. Well, okay, fine. He can use passive, all right? But if this is pushing that way, this is pushing this way. So is it really passive? If this becomes active and dynamic, then yeah, you could consider that passive. So we won't pick it apart. But let's see. A key also increases the resistance. Oh, he did have a little tiny key there. I got to look at my trifocals better. Well, I put a bigger key in there. Okay. Now, do not take these as gospel. These are the typical rule of thumb, average coefficients of friction of these things, okay, of gravel, silt, dry clay. And no, I'm not going to make you do friction coefficient calculations or structural engineering calculations or anything like that. So don't go jump out a window or something, okay? Trust me. Again, this is an introduction survey course. Yes, I can get geeky with engineering because this stuff's just making me lather all up. This is exciting for me. Woo! Yeah, I love this stuff. And I know some of y'all are throwing up by now. But just bear with us. Okay. Your engineer is going to be doing this stuff. All right. You just, as the architect, need to know if we need a retaining wall like this, what kind of retaining wall it's going to be. And when the engineer says that soils mechanic engineers and us have decided we're going to do this, don't say, oh, this is so ugly. You might actually use this retaining wall as an architectural component of your structure. Because what's the difference between a retaining wall and an exterior basement wall, right? In other words, what happens if you can incorporate this into your building structure? You put a little keyway up here, slab, right? And then you build your building on top of it. Use it as a part of your building wall. Who knows? And you can texture this concrete. You can use forms that have a texture that make it look like brick or stone or vertical stripes or whatever. So this just gives you kind of a vocabulary to talk to your engineer. Let's look at more retaining walls. And y'all are probably saying, no, please don't. All right. Well, we got plenty of time. Oh, yeah. Okay. Reinforced concrete retaining walls. Now, these are reinforced concrete retaining walls. I don't like wood retaining walls. They're a waste of money. Masonry retaining walls are a waste of money, in my opinion, unless that's all you've got. If you've got a bunch of concrete block and some cement, and that's all you've got, that's fine. But you better engineer that and reinforce it good. All right. Yes, reinforced concrete's expensive. I think it's running $175 to $180 a cubic yard right now for 3,000 psi. No, 4,000 psi concrete. But the upfront cost is one thing. The life cycle cost of this, trust me, if this stuff busts up, if your engineer, your structural engineer did this right, and your geotechnical engineer did his soils mechanics right, this will be here way into the next century. There are reinforced concrete structures that the Romans did during the Roman Empire that are still in existence today in the Mediterranean. And they didn't have the modern day cement that we had. The Romans used fly ash. That's volcanic ash out of those volcanoes as their cement. Their pozzolan. It has calcium carbonate in it. It's naturally hydrating. And yes, I'm getting off into geek land. And but now, when the coal-fired power plants came on, they had a ton of fly ash left over. So we started using fly ash to mix it with the cement for reinforced concrete. I was on a committee back in the 70s with the American Concrete Institute, and that was a big thing. We used fly ash mixed with the cement in the concrete, and we got the same strength concrete, same density concrete, and we were reusing. Remember that LED thing on the chapter 1 video about reusing materials? Well, we're taking something from power generation, fly ash, and we're mixing it with cement. So we didn't have to use so much cement because it takes a lot of energy to make Portland cement. And the Romans did not have Portland cement. They just had fly ash. And their cement structures are still in existence in the Mediterranean. exposed to salt water. What about their aqueducts? Yeah, so don't discount that. All right, so you learned some history. All right, gabions and pozzolans. That means it hydrates water and gets hard. Okay, all right. So different types of reinforced concrete retaining walls. A gravity wall is just because it's a big chunk of concrete. Okay, see, it has no foot, has no key. It's just a big block of concrete stuck in the ground. Okay, all right. Here is a T-type cantilevered wall, and it's cantilevered. Why is it cantilevered? Because this is a cantilever. Okay, there's nothing supporting this up here at the top, so it's cantilevered. And the forces over here makes it want to go what direction? Makes it want to go that direction, this direction. And it makes it want to do what? Rotate over. There's the moment. And where was it? At 1/3 the height, right? Okay, all right. And then we've got the resistance forces over here, blah, blah, blah. And if you really want to get fancy, you could put you a giant key down here, concrete in there. Here's a reinforcing steel. And okay, I'll shut up. All right, so let's move on. Counterfort. This is called a counterfort wall. It's like a T-type cantilevered wall, but it utilizes a triangular shape, cross walls, to stiffen. Okay, that's what this does. This works like a baffle or a shear wall. We'll get to shear walls when we talk about buildings, but that's all this really is. It's just acting as a shear wall, and it reduces the span. And we'll talk about that when we get to two-way concrete slabs. Yeah, and you just thought I was another pretty face, didn't you? Okay, all right. See, it reduces the span. So what happens if you have a long wood beam and you have a support here, and you're going to load the beam that way, and it's going to sag more, right? But if you come out here in the middle and you stick another column, then it doesn't sag as much, and it'll carry more weight. And that's all this is doing, except it's in a wall. And it's no different if it's the wall in a vertical or if this was an overhang. All right? Force is force. All right, so that's called a counterfort wall. And this is a T-type. This is a counterfort. And this is a gravity wall, because this is a big giant chunk of concrete. Okay. All right. And he's got some rules of thumb in here. All right. Let's see, an L-type. Okay, this is an L-type cantilevered wall. Guess why they call it an L? Because it's in the shape of an L, right? Yeah. Go figure. All right. This type of retaining wall is used when the wall abrupts a property line or other obstruction. In other words, let's just say this was a property line right here. Okay. Hopefully this is your property. Here's the property line. Property line. Wow. Okay. Property line. All right. That way, why? Because your retaining wall is going to have all this weight on it, right? It'll help. Okay. Okay. If this is the property line and you're over here, this is your property, UP, then this foot's going to have to get longer than that foot, all right? Because you don't have as much weight on it, okay? Or you may have to sink a footing down here or something. Keep it from overturning, all right? Okay. Drainage systems may be required to relieve the buildup of water pressure behind the wall. That is true. You may need that depending on the soil mechanics and the nature of your subsurface topography. Remember, topography is not only up here, it's also what's happening down here underneath the surface. So the drainage mat, okay, with filter fabric, porous gravel fill, and they say use a 2-inch pipe, but your engineer is going to tell you what you're actually going to use, and you may have to have weep holes through there, okay? All right. Now, if you are having a water problem and he doesn't show that here, you may actually need a water stop. which is a impervious thing in here to keep any migration through there. All right, it depends. Your mileage is going to vary. And he talks about it should exceed 2 feet below the frost line. We don't have a frost line down here. Let's see. What is he? He uses the term batter. The backward sloping. Yeah. Okay. That's another term. A batter means it slopes backwards. Temperature still for walls. That's just minimum percentage of steel. That keeps the surface cracking down. When an engineer refers to temperature steel, he's talking about the minimum area of reinforcing steel per thickness of concrete. And that is not structural steel reinforcement. That is concrete reinforcement. But that's fine. It's still part of the concrete, reinforced concrete. They don't refer it as structural steel. It's rebar, okay? It's for reinforced concrete. And you'll see this J-hook, JL coming up. They'll pour this foundation, and then they'll probably tie the vertical rebar to it. Unless it's short, then they'll run it all the way up. All right. He talks about vertical control joints at 25 feet on center and vertical expansion joints every 4th control joint. What he's talking about is this wall running that direction. So let's just say we had this wall. We had this wall like this. So rule of thumb is you want a vertical control joint every 25 feet, and then an expansion joint every 4th control joint. So let's just say where's 4. Then this, it would be your expansion joint, which would allow the wall to expand. It would have some expansive material and a water stop in there to allow it to slide, probably an elastomeric water stop, which would allow the wall to theoretically move this way and this way. And depending on how you reinforce the wall, you might get by with longer than 25 feet, but it depends on the calculations from your engineer. And a control joint, and this is a construction joint. This is a construction joint, not a control joint. Okay, all right. I think we have beat that up enough, especially since you're architects and not engineers. But you need to know these terms so you can talk somewhat intelligently to your engineer. Come on, where are we at? 32 minutes? Okay, well, we're fine. Timber and concrete, brick, and stone masonry may be used for relatively low retaining walls, and retaining walls that you don't expect to be there forever. Okay, heavy timber, cross ties, railroad cross ties. You're going to have to drill through them, and you're going to have to tie them together, screw them together, nail them together, whatever. And you're going to have to hold this wall back with a dead man. Okay, that's buried back in here, and hopefully this horizontal tie is designed back to these dead men properly. A dead man is a timber, stone, or concrete mass buried in the ground. And it's an anchor used for walls over 3 feet high and placed 6 feet on center. Rule of thumb, your soils engineer and your structural engineer, if he's gotten over the fact you're going to make him build one of these, design one of these, will tell you what you need. Again, these are for relatively low, and don't expect them to last forever. And unless they are constructed properly by the contractor, they're going to be a maintenance headache. They will be. Now, if that's all you can do, then that's all you can do. All right. This talks about this, okay? All right, so that's a horizontal timber wall. Brick or stone coping. These things need weep holes because you're going to have latents. The water penetrating through this soil. He doesn't talk about latency in here, but I'm going to talk about it. It's leaching the calcium out of the mortar. And I don't care what kind of mortar you use, it will eventually leach out. But depending on how much hydrostatic pressure is behind here over the years, you will need a vapor barrier on this, which means you'll need to paint the back of this with coal tar epoxy or line it with something heavy elastomeric, and then seal your weep holes. I am not a big fan of concrete masonry and brick veneer retaining walls. I'm just not. These are for very short walls. I'm telling you, short walls with not much moisture behind them, not much water pressure behind them at all. They can look cool, but the problem with them is you're going to have to design this masonry as structural masonry, which means these things are going to have reinforcing bars up through the CMUs, the concrete masonry units. You're going to have tiebacks all the way through here, ladder ties back in, and if not, you're going to end up having a maintenance headache. And then the capping, brick or stone cap, I think the cheapest thing to do would be to do a cast in place concrete cap, but you still got your joints. So anyway, I'm not a big fan of these, but there are a lot of them around. These low landscaping ones, like for planters and stuff like that. But you watch them. You can find some old ones and you'll see how they start pulling apart, especially down here. Now, all right, this is a battered stone. What was the batter? It's a backward slope, right? The batter is the backward slope, okay? In other words, the top is narrower than the bottom. So the batter is a backward slope. All right, yeah, so you're going to tilt these stones, and you're going to find you a stonemason that can build these. Now, if that's all you got is stones, and you got to build one of these, well, you better use some epoxy-based mortar, and try to get some reinforcing in there some way, somehow. I've seen some of these where they've had to go back in and to save them, they had to put structural elements on the outside, and they had to drill tiebacks back in the soil with the dead men. They had to dig down in here and do tiebacks to hold this stuff from falling apart. So anyway, paving. Paving, we could spend a whole semester on this, but we're not going to. This describes the strata of paving. You got your top coat, which carries the wear. You've got your what I call the base, which is your foundational element, and this is your subgrade, which is your main structural stuff. And depending on what your base is, that's going to transmit the load to your subgrade, and it also prevents upper migration, hopefully, of capillary water, because it'll allow it to run through here. Now, all pavements are considered flexible. Even the reinforced concrete roads that you drive over, civil engineers refer to that as flexible pavement, because it does flex a little bit. You don't notice it flexing, but it does flex a little bit. And in the superheat, like this last summer where we had, 3 months of triple digit, some of the concrete pavement popped at the construction joints and expansion joints. So you could spend a whole lifetime becoming a subject matter expert on flexible pavements. Rigid pavements, such as reinforced concrete slabs or paving units mortared over a concrete slab, distribute their loads internally and transfer them to subgrade over a broad area. They require reinforcement and an extension of the base material along their edges. So now Ching, he separates. I said even a reinforced concrete slab was flexible pavement. Well, as a civil engineer, that's what we refer to your concrete roadways. But he's giving you, and as an architect, he's right. Okay, I'm not arguing this at all. Okay, because this doesn't have reinforcement through it, right? So he's calling this flexible. This all flexes, moves, whereas a reinforced concrete slab, let's just say we have a reinforced concrete slab, and we'll put our reinforcing steel in the center. Okay, and there's your reinforcing steel, poorly drawn, but we're not using AutoCAD. So, all right, we got our tie steel. Okay, yes, this is this is more rigid, but still it's going to flex due to heat. Not much. If it flexes a lot, it's going to crack. Okay, so don't get confused and don't get too argumentative. But as cars run over, let's just presume this is a piece of reinforced street. This is a cement truck, okay? As it's moving, okay, you got a lot of heavy load here, right? So, but you don't have any load here. So, yeah, this is going to flex a little bit like that. And then when the truck moves over here, this will come back up. Now, not much, but some. Okay? All right. There's no extra charge for that. So, flexible pavements are like masonry units. Use this definition. And then rigid pavements is that definition. And everybody will be happy. You'll be happy, I'll be happy. Now, God, look at all these test questions. Oh man, you could drive somebody absolutely to the insane asylum with all these types of pavement. Look at that. Wow. And here's the details. Okay? On the edge, you're going to need a giant paving unit, mortar, that kind of thing, right? Okay. So these are all the details. So study these details. If you're going to go into architectural design, and if I remember looking at the roster, every one of you are, then this is your vocabulary. This is your visual vocabulary of what you're going to be doing. Is it mandatory right now that you memorize all this stuff? No. That's why you have this book. You keep this book. Okay? Here's a running bond of masonry. You see, every joint hits a solid piece. Every joint hits a solid. Every joint hits a solid. Here's a stack bond. Now, if you did me a stack bond, I'll fire you. Because this is not structurally sound at all, especially in a wall. You do a stack bond on a wall, you need to be fired. Go work at Walmart. Okay? But for paving, you see a lot of this. What they'll do is they'll come in here and leave a little gap in between all of this. They'll even leave gaps in between this. And they'll come in there and they'll sweep Portland cement in here. They'll sweep Portland cement in between the cracks. And then they'll come in and they'll hose the stuff off and let the Portland cement hydrate and seal up the cracks. Interlocking basket weave, octagon dot, Roman cobble, random stone. Easiest thing to do is cast these things in big 2 foot by 2 foot concrete blocks so it looks like this, and then lay them in. Okay. There's all kinds of pavers. Grit or turf block. This was really popular for parking lots where people wanted green space. So what they do is they just interlock these on a good substrate, come in and put topsoil in these little holes, and then plant grass. And the grass would grow out of here. They'd come through and mow the parking lot to keep the grass down, and cars would park over this. Okay. Here's an example of the turf block. Okay. All right. So yeah, you have a sectional example of these up here, which is good. This again is your design vocabulary. Okay. Now, how much time we got left over? Because we're going to finish this. All right, we're at 45 minutes, so we'll extend this out. Here's a site plan. Okay. Here's everything that needs to be on the site plan. Everything. There are 20 things that need to be on the site plan. Okay. I know what some of y'all are thinking. Oh my God, these exams are going to be horrible. He's going to ask us to list 20, blah, 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 blah. Just chill out. There's no way. Because if I ask you all these questions, then I got to grade all these questions, right? So everybody just chill. Okay? All right. So don't get all freaked out. And like I said, if I create something that's not working, I'll uncreate it and we'll get something that'll work. You got student learning outcomes to do, and as long as we hit those, I'm happy. As long as you learn them and you keep this book and move forward and continue to learn. Because you ain't going to remember all this. I don't care if it was 16 weeks long. Okay? But the site plan needs to have those at least 20 things on them. Okay? Now you know where to go find it. All right? So you read down through all of here. It needs to have in the north arrow. Oh man, that's my biggest pet peeve. Somebody give me a drawing for a site plan and that building's not located. There's no north arrow. Oh, that drives me crazy. Here's your north arrow up here. Okay. And the scale. We'll want a scale. And here's your note block. Here's topo lines. Looky here. All right. And 15, location of existing utilities. So the site plan in your book with these numbers, 1, 2, 3, 4, 1, 2, 3, 4, legal description of property, all that is tied to these items here. Okay? So study this. Study this. If you're going to do a site plan for a project in one of the other drafting classes, make sure that you cover all these things. See, here's a topo lines. Now this one does not have setbacks. It needs to have setbacks. It needs to have setbacks. Okay? All right. And this talks about the legal descriptions and the rectangular survey of surveying, and we're not going to go into that. It talks about what a section is. All right. And that sort of stuff. All right. Principal medians are north, but it gives you kind of an idea of what surveyors do and go through. Now let's look at 20. Look at that section right there. Let's go back over here and look at your description. References related to drawings and details. Right? So what does that look like? You're going to pull elevations off of this, right? Your floor plan had better look sort of like this. Then your sections come off of that. So that pretty much ends the third video of chapter 1. Wasn't that painful? Yeah, we're at 48 minutes. Oh my God. So this is kind of surveying, baby surveying 101, all stuff down here. Okay. So what surveyors go through, what civil engineers look at when they look at the meets and bounds. See? Meets and bounds. I used that term earlier in one of the videos, maybe this one. Okay. And it talks about all that. When you go buy a house, you should get a meets and bounds. You should get a property description. If you didn't, somebody's pulling a game on you. Okay. And it should have everything. It should have the easements, the length of your lot, your setbacks. It should have everything. Okay. We will see you on chapter 2.